vanishing ideal. So people who are familiar with that will actually will know it very clearly. But let me just give an idea of the vanishing ideal of what it is. So if we have a set S, which is there, let's say in K of n, where K is a field, then the vanishing ideal of the set S is defined as all those polynomials which lie in the polynomial ring with variables, say x1 to xn, such that f of s is equals to 0 for all s lying in the set S. So let's look at an example for this. So let's say we have S to be the uh, set of 2 points, and let's say Q2, so that are the rationals. Let's say they are like 1, 1, and 2, 3. Then the vanishing ideal would be defined as the ideal which is generated by these product of 4 terms, that is x1, x minus 1 times y minus 3, and x minus 1 times x minus 2, and y minus 1 times x minus 2, and y minus 1 times y minus 3. So the reason that we get this is something like this. So for example, if you take consider the point 1, 1 and plug it in any of the polynomials over here. Let's say we pick up the first one and plug in 1, 1. Then as we can see, if we plug in x equals 1, this first term will become 0. So this entire polynomial becomes 0. Similarly, if we take, let's say 2, 3 and plug in any polynomial over here, let's say the third one, then we see that when we plug in x equals 2 over here, this term becomes 0. So this entire term becomes 0. So that's the idea of a vanishing ideal, that these points are basically the solutions of the generating set that we have over here. Okay. So that's the concept of vanishing ideal, which we'll be using throughout my talk over here. So
Sorry, Pratik, I have a question.
yeah,
The vanishing idea is a set of these polynomials, or is it the ideal generated by these polynomials?
it's the ideal generated by these polynomials.
In the definition, you have a set.
Yeah, the S is uh, the vanishing ideal is defined on a set, but that is an ideal. So
Okay, thank
that's the
you.
thing. Like we have the ideal generated by these 4 polynomials by the basically by the property of ideal. So if you pick any element, uh, the point 1, 1 and 2, 3 would be satisfied by those points, by those elements inside. Okay. So let's move on to a simple definition of complete graphs. So a graph G is said to be a complete graph if there exists an edge between any 2 vertices of G. So this is a pretty common definition. So now let's look at the concept of toric ideal. That is something that will be used throughout over here. So the toric ideal is defined by using a matrix. So let A be an n cross n matrix with integer entries. Then the toric ideal corresponding to the matrix A is defined as the ideal generated by the set of binomials of the form x to the u minus x to the v, where u minus v lies in the kernel of A. So in other words, we can say that the toric ideal corresponding to A is the ideal generated by x to the u minus x to the v, where A times u minus v is basically 0. So let's look at an example for this concept. So let's consider this matrix, this 3 cross 5 matrix. Then the toric ideal, when we compute the toric ideal corresponding to this matrix, we get something like this. So over here, we can consider the columns corresponds to, let's say x1, x2, x3, x4, and x5 respectively. So we get the vanishing the toric ideal as x1, x3 minus x2, x4, and x1, x4 squared minus x3 squared, x5, and so on. So let me just explain how these generators come over here. So if we look at the first generator, we have x1, x3 minus x2, x4. So for this generator, we have corresponding vectors u and v, where u basically looks like this, which is we have 1 at the first and the third position and 0 elsewhere. And this basically corresponds to x1, x3. Similarly, we have v, which has a 1 and which has 1 at second and fourth position and 0 elsewhere. And this corresponds to x2, x4, right? So if you observe that if you look at u minus v, it would basically be 1 minus 1, 1 minus 1, 0. And when we take the product of A times U minus V, that is basically 0. So that's uh, the general concept of toric ideals. So yeah, any questions so far? All right. Now that we have some preliminaries of algebraic geometry and a little bit of graph theory, so let's look at the concept of Gaussian graphical models, how the problem is set. So for this, we have a graph G, which is like an undirected graph with, let's say, vertex set with n vertices and edge set E. Then using this graph, we define a subspace L that is generated by the matrices Kij, which has 1 at the ijth and jith position and 0 elsewhere. And these Kijs basically come from the graph. That is, we take all this set of Kijs where ij is basically an edge in the graph G. Okay, so using the subspace L, we define a set called L inverse, and that's defined as all those symmetric matrices whose inverse lies in L. And the homogeneous prime ideal of all polynomials in the polynomial ring of R sigma that vanish on L inverse is denoted by P sub G. So in previous example, when we saw the vanishing ideal, we computed the vanishing ideal for this set of points, but over here, we'll be computing the vanishing ideal for the set of matrices. So that's the concept over here. So I'll give an example for this, but before that, let me just explain the problem that we're working on. So for a given, is there any question? Okay. Uh, so yeah, so the problem over here is that for a given graph G, we want to find the generating set of the vanishing ideal, that is a vanishing ideal of PG. Now, one way to compute the vanishing ideal is to eliminate the entries of the matrix K from the system of equations, which is obtained from the fact that sigma times K is equals to identity, where K is the generic matrix in the subspace L. Okay. So let's look at an example for this. So let's consider this graph with 4 vertices. Then the corresponding covariance matrix, which is sigma, would look something like this. So that would have entries sigma 1, 1, 1, 2, 1, 3, 1, 4, and so on. But the concentration matrix K, that is obtained from the graph. So observe that we have entries K 1, 1, 1, 2, 1, 3, but we have 0 at 1, 4, and 2, 4 position. Now this comes from the graph because if you look at the graph, we see that the edges 1, 4 and 2, 4 are missing in the graph. And correspondingly, we have a 0 at 1, 4 and 2, 4 entries. So that is how the generic concentration matrix is obtained from the graph G. Now, as I said in the previous page, that the vanishing ideal can be calculated using the equation that sigma times K is identity. So what we do is we look at this matrix sigma times K minus identity and take all the entries of that and perform a process of elimination. So by eliminating the Kij variables, all we'll be left is the variables in sigma ij's, and that gives us the vanishing ideal for this model. And over here for this graph, we have the vanishing ideal, which looks something like this. So this is generated by sigma 1, 3, sigma 3, 4 minus 1, 4, 3, 3. And we have 2, 3, 3, 4 minus 2, 4, 3, 3. And we have 1, 4, 2, 3 minus 1, 3, 2, 4. So if people can see over here is that like these generators are basically the 2 cross 2 sum of the 2 cross 2 minors of the covariance matrix sigma over here. And that is something which we'll be looking into it in more detail. Okay. So is the problem clear with everyone? So any questions so far?
Yeah, what did you mean by covariance matrix? Why do you call it covariance matrix?
So that's basically the matrix that we are working on. So the covariance
Uh,
matrix is the sigma, and its inverse is basically the concentration matrix, and that is obtained from the
Inverse?
graph G. So I'll not really get into the details of that. So I mean,
Okay.
that's how the terminology is defined over here.
So K is like well, okay, K is your sort of adjacency matrix. It
Yep, yep,
counts,
yep.
right?
Yeah, it comes from the graph.
Okay. And what did you mean by eliminating Kij variables?
So that's a concept in algebraic geometry that once we have these variables in the generating set, what we can do is we can like apply a process of elimination. Over there, what we do is we eliminate the Kij variables that we have in each of the generating set, and the remaining thing that we get is an ideal in only the variables of sigma ij's.
Okay.
Okay.
So, do you mean by eliminating you are homogenizing it? That's what you mean?
Not really homogenizing it. I mean, not necessarily that every time it will be a homogeneous polynomial or something, but so there's like a series of polynomial, I mean, I
No,
have to
no.
go through
I
the
mean,
entire algorithm over here then to explain the
okay,
process of elimination. So yeah.
okay.
Any other questions? Okay. So now the process of elimination over here is like computationally expensive. So instead of using this elimination, we express the vanishing ideal in terms of kernel of a map, which is a rho star G. And the map is defined something like this. So we have this map from the polynomial ring in sigma ij's to the polynomial ring in k ij's. And basically, rho star maps sigma ij to the ijth entry of k inverse. So over here that we saw that we have this equation that is sigma times k is identity. So in a way, we are basically mapping sigma to sigma. Basically, k is the sigma inverse over here, right? So that's the map that we use, and we multiply 1 over determinant of k to like make things a bit simpler because this will be a constant term and won't really affect the kernel of the map. So that's how the map rho star is defined. And the vanishing ideal can be written as the kernel of this map. So let's look at the same example that we computed in the previous one. So for this graph, the map rho star would be given something like this. So we have, let's say, sigma 1, 1. Then sigma 1, 1 is basically mapped to the 1/1th entry of K inverse. Similarly, sigma 1, 2 is mapped to the 1/2th entry of K inverse, and so on. And that's how the map is defined. And computing the kernel of this map is of comparatively less expensive than computing the elimination process. Okay, so that's how a general vanishing ideal is obtained for a model. Now let's look at some terminology for of graphs. So if you have a graph G with vertex set V and at set E, and let's say ABC be some disjoint subsets of the vertex set such that its union is the entire set V, then we say that the set C separates A from B if for any A in A and B in B, any path from A to B passes through a vertex in C. So this is like a generic definition of separation. Now, a set C is called a clique of the graph if the subgraph induced by C is actually a complete graph. Now, a graph G is called a C-clique sum of smaller graphs, say G1 and G2. If there exists a partition ABC of its vertex set such that C is a clique with cardinality being, let's say, small c, and C separates A and B, and the subgraphs G1 G2 are basically the subgraphs induced by A union C and B union C. So let me just give an example for all the definitions that we saw so far. So if we consider this graph with say 5 vertices, and let's say A as the set 1, B as the set 4, comma 5, and C is the set let's say 2, comma 3, then we observe that every path from 1 to let's say 4, there are basically 3 paths from 1 to 4. That is, we can go from 1 to 2, then 2 to 4, or we can go from 1 to 3 and then 3 to 4, or we can go from 1 to 2 or 2, then 2 to 3, then 3 to 4. So any of the 3 paths, we observe that it has to pass through either 2 or 3, right? Similarly, if you look at all the paths from, let's say, 1 to 5, then that's also the case for 1 to 5 as well, that it either passes through 2 or 3 or both. So we can say that now, okay, so if you look at the subgraph induced by 2 comma 3, that's the set C, then that's basically an edge connecting 2 and 3. So by subgraph induced by 2 and 3, I mean that I remove the vertices 1, 4, and 5 and just look at the subgraph that is induced by 2 and 3. So that's an edge over here. So that's basically a complete graph in two vertices, right? So that is a clique. So by a definition, we can say that G can be written as a two-clique sum of G1 and G2, where G1 is a subgraph induced by 1, 2, 3, which is A union C, and 2, 3, 4, 5, which is B union C, and that's denoted in blue and red respectively. Okay. So yeah, any questions or something? Okay. So
Yeah, in that the previous picture, G1 also included the edge 2, 3, right?
yep, yep.
Okay. The
So
2,
we
3 is like a common edge of
yes,
red and blue.
yep, yep, yep. So we have inducing G1, G2 are, but G1 is basically induced by A union C, and G2 is the subgraph induced by B union C. So C is a common part between both G1 and G2. Okay, so this brings us to the concept of conditional independence. So we use a proposition over here which says that if x is, let's say, x1, x2, xn be a Gaussian random vector, and if ABC be a subset of n that are pairwise disjoint subsets, then we say that xa is conditionally independent of xb given xc, and that is basically denoted by a conditionally independent of b given c, if and only if the submatrix of the covariance matrix sigma, which has got rows A union C and columns B union C, that has the rank which is same as the kernelity of C. Now, using this, we have something called the Gaussian conditional independence ideal. So that is defined for every conditional independence statement, and that is given by that is basically an ideal which is generated by all the C plus 1 minors of sigma A union C B union C. So if we have, let's say, a graph G which is undirected, and I have a partition ABC with C separating A from B, then the conditional independence statement, that is A conditional independent of B given C, holds for all multivariate normal distributions where the covariance matrix sigma is obtained from the graph. So using this conditional independence statements, we define something called as the conditional independence ideal for a graph, and that is defined as the ideal which is generated by all the Gaussian conditional independence statements, and we take the sum over all the possible conditional independence statements that is obtained from the graph. Okay, so in terms of graph G, the conditional independence ideal is basically the set of determinantal constraints that is obtained from the zeros of the concentration matrix K. So I'll get into this in the next one with an example. Before that, let me just give an important proposition that we have. It says that if ABC is a separating partition of G, then the rank of the submatrix sigma A union C, B union C of the covariance matrix sigma has a rank which is kernelity of C. And hence, the generators of the conditional independence ideal vanish on the matrices in L inverse. So in other words, we can say that if we take any generator of the conditional independence ideal, then the matrices that we obtained in L inverse actually satisfy those generators. So we can basically say that the conditional independence ideal is always contained in the vanishing ideal. So let's look at an example for the conditional independence ideal. So let's consider the same graph that we have been seeing so far. Then if we take, let's say, the set A as 1, 2, and B as the set 4, and C is the vertex 3, then we see that C separates A from B because let's say if we look at all the paths from 1 to 4, there are basically two paths from 1 to 4, which either can be from 1 to 3 and then 3 to 4, or it can go from 1 to 2, then 2 to 3, and then 3 to 4. So in either case, it passes through the vertex 3. Similarly, all the paths from 2 to 4 also passes through the vertex 3. and there's no other separation that we can have over here. So the fact that 3 separates 1 comma 2 from 4 is the only separation criteria that we have. So from
Wait, wait,
there,
wait. Sorry, sorry. So why
yep.
can't C be 2, 3? It will also separate 1 and
So
4.
that's true, but we consider the minimal separating set.
Okay.
So we're taking, so yeah, the way the conditional independence is defined, so that's basically a rank constraint that we're obtaining. So if we take 2 comma 3, that is also fine, but it's just that the generators that we get from here is basically contained in the generators that we get when we take CS3. So using this separation, the conditional independence ideal is basically defined as the 2 cross 2 minors of sigma A union C, which is 1, 2, 3, and a B union C, which is 3, 4. And we're taking 2 cross 2 minors because the way that we define conditional independence ideal over here was taking the C plus 1 minors of the matrix. And over here, C is just the set C, just the set 3. So we take 2 cross 2 minors. So as we can observe over here, we get the 2 cross 2 minors, which look something like this. That is 1, 3, 3, 4, 1, 3, 3, 4 minus 1, 4, 3, 3, and 2, 3, 3, 4 minus 2, 4, 3, 3, and 1, 4, 2, 3 minus 1, 3, 2, 4. And as I had shown earlier, that is exactly the vanishing ideal that we obtained for this graph. So in this case, the vanishing ideal and the conditional independence ideal are actually the same. So an obvious question that arises over here is that are these two ideals equal for all graphs? And unfortunately, the answer is no. So the reason being, we computed the vanishing ideal for this graph with 7 vertices, and we observed that we got this big polynomial that was present in the vanishing ideal, but that was not present in the conditional independence ideal. So so the next question that arises is that for which class of graphs are these two ideals equal? Now, to answer this question, we need to define something called as the one-click sum of complete graphs. Now, a graph G is called a one-click sum of complete graphs if there exists a partition of its vertex set, let's say ABC, such that the cardinality of C is 1, and C separates A and B, and the subgraphs induced by A union C and B union C are either complete graphs or are one-click sum of complete graphs. So there's another definition of central vertex. Before I get into an example, so a vertex C is called a central vertex if there exists a one-click partition ABC with C being the set C. Okay. So let me just give an example for this. So let's consider this graph with 6 vertices. So if you consider the partition ABC where A is the set 1, comma 2, B as the set 4, 5, 6, and C as the vertex 3, then observe that the subgraph induced by A union C, which is basically 1, 2, 3, is a triangle, and that's a complete graph in 3 vertices. Now, similarly, if you look at the subgraph induced by B union C, that is 3, 4, 5, and 6. So that is not a complete graph, obviously, but that can also be seen as a one-click sum of complete graphs. If we consider the partition A1, B1, C1 as 3, 4, and let's say C as 5, and B as the vertex 6. So we can basically see the subgraph induced by B union C as gluing a complete graph with 3 vertices, which is the triangle of 3, 4, 5, with the complete graph with 2 vertices, that is 5, 6. So from the definition, we can say that A union C is a complete graph and B union C is a one-click sum of complete graphs. So G is actually a one-click sum of complete graphs. So there's
Hold
another
on.
part.
Something.
Uh-huh.
Uh, I mean, like if you break it all up into single vertices, a single vertex with no edges is also complete graph. Then anything will be a. So what? So thinking something wrong maybe.
So
Like any graph is a union of single vertices, which are all complete graphs. So
no, but when you take single vertices, you're deleting the edges there. So that is not how you decompose them. So you'll have to keep the edges intact.
okay.
Yeah. So when I'm saying like subgraph induced by 1, 2, 3, I can basically keep all the edges 1, 2, 2, 3, and 1, 3. But I do not have to delete any other edges when I'm decomposing them, right? So that's why we're not like decomposing single vertices. We're decomposing a group of vertices.
Thank you.
So that's the concept. So similarly, we have another partition for this graph. Let's say if we take A as 1, 2, 3, and 4, and C as the vertex 5, and B as the vertex 6, then that would also be a one-click partition for this graph G. So from the definition of central vertex, we can say that both 3 and 5 are the central vertices for this graph. Okay. So this brings us to the main conjecture that we worked on. So this is a conjecture given by Sturmfels and Euler in one of the papers in 2009, which says that the prime ideal PG of an undirected Gaussian graphical model is generated in degree at most 2 if and only if each connected component of graph of G is a one-click sum of complete graphs. Now, in this case, the vanishing ideal has a Grosvenor basis consisting of entries of sigma and the 2 cross 2 minors of sigma. So in order to prove this conjecture, our aim was to first show that the conditional independence ideal is equals to the vanishing ideal when G is actually one-click sum of complete graphs. The reason was in the case when G is actually a one-click sum, the conditional independence ideal can be written as the 2 cross 2 minors of sigma A union C B union C, where we take the union over all the possible one-click partitions of the graph G. Now, if you could show that the vanishing ideal and the conditional independence ideal are actually same in this case, then that would basically prove the conjecture that we have. So we have some useful results that we used using the properties of one-click sums. So the first result is that if G is a one-click sum of complete graphs, then there exists a unique shortest path between any two vertices of I and J in G. So we denote this unique shortest path between I and J by this double arrow symbol. Now, if ABC is a one-click partition of G with C being the vertex C, and let's say if I is a vertex in A and J is a vertex in B, then we could show that the shortest path between I and J actually decomposes into a shortest path from I to C and then a shortest path from C to J. So the next point is really important over here. So if you consider the set F, which is the set of all polynomials like Fij, where each Fij is basically the determinant of k times the ijth coordinate of k inverse. That is something that we used earlier to define the vanishing ideal. Then each of these polynomials Fij had one of the terms which looks something like this, so that we have the product of k I prime j prime, where I prime j prime is an edge in the shortest path, times k tt, where t is not an edge in I to j as one of its terms. So let me just explain what I meant over here. So if we consider this same graph that we saw earlier, then if we take the matrix K corresponding to this graph and compute, let's say, the 1/2th entry of K inverse, then we would have the monomial as one of its terms, which looks something like this, which we have K12 times K33, K44, K55, K66. And this corresponds to the shortest path between 1 and 2. So over here, we can see that the shortest path from 1 and 2 is basically the edge connecting 1 and 2, right? So corresponding to that, we have this term that is K12 and the remaining terms as the diagonals, which is K33, 44, 55, and 66. Similarly, if we compute, let's say, the 1/4th entry of K inverse for this graph G, then we got this term as one of its terms, that was K13 times K34, and the remaining terms as the diagonals, which is K22, K55, K66. So yeah, it might be a good point to stop and ask if there is any questions so far. All right. So this observation actually allowed us to construct something that we call as the shortest path map. Now, the shortest path map is given by psi of G, and that is basically a map from sigma ij's to kij's along with some new variables ai's, where we basically replace kii with ai. So we're just replacing k11 with a1, k22 with a2, and so on. And the way the map is defined is that sigma ij is mapped to ai times aj times the product over ki prime j prime, where I prime j prime is actually an edge in the shortest path of I to j. And it's mapped to ai squared when I is equals to j. So let's look at an example for this. So if we consider this graph with 4 vertices, then the shortest path map for this graph was basically defined as sigma 1, 1 being mapped to a1 squared. And if we, let's say, consider sigma 1, 2, then that is, we look at the shortest path between 1 and 2, and that's the edge between 1 and 2. So we have the endpoints a1 and a2, and the shortest path corresponding to it, that is k1, 2. So similarly, if you look at, let's say, sigma 1, 4, then we know that the shortest path from 1 and 4 is basically the path from 1 to 3, and then from 3 to 4. So the corresponding image in the shortest path for sigma 1, 4 was basically a1 times a4 times k1, 3 times k3, 4. So that's how the shortest path map is defined. So the interesting thing that happens over here is that when we saw the original map that we had, that is rho star, that was taking sigma ij to the inverse entry of the k, and so that was basically a non-monomial map, right? That was basically a polynomial. But over here we have that each of these elements are being mapped to a monomial. But in the case of one-click sum of complete graphs, when we compute the kernel of both these maps, these are actually equal. So that was our basic concept for proving the conjecture. So this brings us to the final result that we had, which says that the conjecture is given by Sturmfels and Uhler is actually true. So the idea for proving this was using basically the shortest path map psi of g. So once we have that the unique shortest path exists, we could define the shortest path map. So the first thing that we showed was to show that the kernel of the shortest path map is actually equals to the conditional independence ideal. And the way that we showed is we first proved this result for all one-click sum of complete graphs having exactly one central vertex. So what I mean by that is if we consider this graph, then we see that 3 is the only central vertex over here. So this comes in the category of graphs with exactly one central vertex. But if we consider, let's say, this one, then we saw earlier that 3 and 5 are both central vertices. So this is something that we do not count in our first case. Now, once we have that result for all one-click sums with exactly one central vertex, we could generalize this result for all one-click sum of complete graphs by using the connection between the generating sets of the toric ideals and the connectivity properties of the fiber graphs. So that is fairly technical. I won't really get into it. Now, once we have this equality that the kernel of the shortest path map is equals to the conditional independence ideal, we show that the dimension of both these ideals are actually equal. And that would give that basically gave us that the vanishing ideal and the conditional independence ideal are actually the same. So yeah, this brings us to the summary of what we covered so far. So the conditional independence statements are not always enough to determine the vanishing ideal of the undirected Gaussian graphical model. And the vanishing ideal is has generators in degree 1 and 2, if and only if G is the one-click sum of complete graphs. And when G is a one-click sum, the vanishing ideal can be determined by obtaining the kernel of the shortest path map. So here are a few references, and yeah, that's all I have to present for today. I'll be happy to take some questions right now.
Yeah, thank you, Pratik. It's time for question and answering.
So what are the like the future directions to take for this notion?
Yeah, that's a good question. I mean, right now I'm currently working on a same problem, but instead of undirected graphs, we are working on directed acyclic graphs. So and we also work on like graphs which have vertices and edges of different colors. So over there, we get some new complications because obviously when we have directions, that becomes a lot more complicated because it is not only kind of restricted to the graphs of one-click sum of complete graphs. It can be more generalized structures over there as well. And when we introduce, like, say, colors over there, we are basically saying that the variables, let's say, the vertex 1 and 2, let's say, have the same color, say, for example, then we're basically saying that the variables k11 and k22 are actually equal. So that brings us a new challenge to this problem. So yeah, I guess those are the few directions that I'm currently working on.
I see. Thanks.
Could you please talk a bit more about that conditional independence? Because I do not understand what that is.
The conditional independence.
Ideal, yeah.
Okay.
What is
So
so? It's like independence is referring to what here?
so that's basically coming from statistics. I won't really get more into it, but I'll most stick mostly to the algebra side of it. So if you consider this graph, let's say, I'll just explain it with an example that will be easier. So if you consider this graph, the conditional independence ideal is basically coming from the separation criteria of the graph. So from separation, as we saw earlier, that we had the separation concept over here, that a C separates A from B using this definition. So using that, we take, let's say, 1 and 2 and B as 4 and C as the set 3. Then we see that 1 and 2 is being separated from 4 by the vertex 3. So from this from this definition of conditional independence ideal, so we take all the C plus 1 minors of sigma A union C B union C. So basically A union C are the set of rows and B union C is the set of columns. So over here we have A union C as 1, 2, 3 and B union C as 3, 4. So, and as we see that C is exactly one element, so we take all the 2 plus 2 minors of sigma A union C B union C. And that's how the conditional independence ideal is defined.
So I should think that A is sort of independent from B.
Yep. Given the vertex C.
I mean, I guess the independence stems from the fact that three, I mean, C separates them, I guess.
Yep. That's how it is C.
So yeah. So what happened with this so what? Okay, now I completed this conditional independence ideal. Could you just go back to the summary again? Okay, now what does this tell me now?
So yeah, I mean, once you have the conditional independence ideal, there are cases when the conditional independence ideal and the vanishing ideal are actually equal, as we saw in the case of one-click sum of complete graphs. But that is not always true in general. So we have this example where the vanishing ideal and the conditional independence ideal are not equal. And I guess, I mean, there are a lot of ways to see conditional independence ideal, but the way that I see is it is important for me because the conditional independence ideal is very much computationally easy to compute. I mean, we computed vanishing ideal using the kernel of the map, but that is still computationally expensive. So once we have this notion that these two ideals are actually equal, then it becomes really easy for me to compute the vanishing ideal of the graph.
And what's the vanishing ideal good for?
So the vanishing ideal, so if you have, I mean, it has got some statistical implications, which I have very less knowledge about, to be honest. But if you have the vanishing ideal generated in degree 1 or 2, then you can actually get back the model just from the vanishing ideal.
You
So you
can
can
get back the
construct
what? Sorry.
the graph basically.
Oh.
So if you do not have the graph, and if someone just gives me the vanishing ideal, and that is, let's say, generated by degree 1 or 2, then I can actually get back the graph from the generating sets itself. And that has got some implications in statistics. Yeah, any other questions?
Okay, if there are no more questions, then let's thank the speaker again. It was a very nice talk, and hopefully everyone enjoyed the talk.
Yeah, thank you so
So,
much. It was really good seeing some known faces. So yeah.
yeah, thank you. It was a very nice talk.
Yeah, thank you. It was many examples, and I understand without even knowing a lot of things.
So that brings us to the end of today's session. So as Indra mentioned in the beginning, that we'll continue this throughout the summer. So we meet again on 11th of June with a new speaker who is also here today. So Pratik Misra will be speaking next Friday, and we'll meet again at the same time. And also, if any of you guys want to contribute a talk, please feel free to send us an email, and I will find a time for you. So thank you for coming again, and have a great evening. Bye. Take care.